Kia ora, Year 12 and 13. I wanted to just do the last question in yesterday's scholarship session on complex numbers because we did it quite quickly in the morning and we didn't really get to it in the afternoon session. So it's actually not an old scholarship question, it's an old level 3 complex numbers question from way back in 2008. And the question has got two parts. The first part is a pretty straightforward merit part. If W is any real number, the equation z to the k equals w has k roots, where k is a natural number, right? So that's what that big N means, natural numbers, 1, 2, 3, 4, 5, and so on. We have to show, for excellence, that the sum of the k roots is equal to 0. So I think that back then, geometric series were taught to most level 3 students. And if you know about geometric series, this question is fine. And if you don't, this question is not fine. So I've done a building blocks video on this a couple of years ago, so go have a look on my channel and find it. It's called, not surprisingly, Building Blocks Geometric Series. But just a really quick recap so that you spot the geometric series that pops up in here. A geometric series is what we get when, to go from one term in a sequence to the next, we multiply by a constant amount. So this one that I'm writing here, every time we move up a term, we times by 1/4. And that ratio is constant, and we call that thing R. We call the first term in the geometric series A. And then it turns out that there are two formulae, and I'm pretty sure I've derived them in the first video. Under certain conditions, we can add up all the terms and they will converge. Okay, so all the terms meaning it goes on forever, but if we were to add up all the terms going on forever, it would add up to the first term over 1 minus r. Now that's not the one we need here. In here, we need the sum of the first n terms, which is this. It's a minus 1 times 1 minus r to the n over 1 minus r. So we're going to use that in the second part of this question. And if you're watching and you kind of got halfway there when you tried it at home, you might have enough now to go on, pause the video, go and try the whole thing. Just need to apologize for the noise. It is the dog who is very, very awake and running around our living room. Okay, so sorry about the puppy. Okay, let's start off by saying that we've got z to the k equals w. As usual, when you're doing something with complex roots, we start by letting z equal r cis theta, and we substitute that in. That's on the left-hand side. Now, on the right-hand side, w is a complex number. Sorry, w is a real number. Right, just going back up here, w is any real number. So if it's a real number, we know that on the Argonne diagram, we can whack it on somewhere on that axis, right? And then when we go to write w in polar form, w will equal w cis 0, but that 0 is not a unique angle, right? So we can write 0, or we could write 360 degrees, or 720, or so on. So in radians, we can say that it's cis 0 plus 2n pi. So I'm hoping that if you're watching this part of it is feeling like I'm going incredibly slowly because you've done this lots of times for level 3 stuff, right? So it's my standard setup for if I'm solving something like z to the power of 4 is equal to 17, right? On this side, we write z equals r cis theta, and on this side, we write 17 cis 0 plus 2n pi. And that's going to let me generate all of the roots that we need. So here we've got r cis theta to the power of k is equal to w cis 0 plus 2n pi. And we now match up the moduli and we match up the arguments. So r to the power of k is equal to w, and then cis of k theta is equal to cis of 2n pi. And this is by de Moivre's theorem. Last time I used the thick orange pen, someone complained, so I'll switch back to k theta is equal to 2n pi. That gives me theta is equal to 2n pi over k. And r is equal to w to the power of 1 over k. So we've got this and we've got this. That means that we can now generate those k roots. So the first root, z1, is equal to the kth root of w. Z2 is equal to that times cis of 2 pi on k, right? So I'm substituting in n equals 1 in there. Z3 is equal to this. And zk, the kth root, is going to be equal to, well, something to do with the 2 pi, right? So this is 2 times 1 pi over k. This is 2 times 2 pi over k. So you can see that the 3 is getting dropped by 1 here. So my kth root will be this times cis of 2 times k minus 1 pi over k. Right, so we've got all of those. Now the next thing we need to show is that they're going to add up to 1. And you can see on your diagram that they are evenly spaced around here, right? So we've got at 40-degree intervals, we've got our 9 roots, and so on, right the way around. Let's now show that we've got a common ratio between two terms. So Z3 over Z2 is a nice easy one to start with. So these simplify away, but then we remember that when we divide complex numbers in polar form, we divide the moduli, but we simply subtract the arguments. So 4 pi over k minus 2 pi over k just leaves me with a ratio of cis of 2 pi over k. Now we can do the same thing all the way through, and if we do the kth term divided by the k minus 1 term, we'd get 2 times k minus 1 pi here over k, and here we would have 2 times k minus 2 pi over k here, and that again is going to simplify to give me cis of 2 k minus 1 minus 2 times k minus 2 over k pi. Now that looks awful, but all we're saying here is that this number is going to be like 8, and this number is going to be 8 times 2 and 7 times 2. So in here, this simplifies to give me just, again, 2 pi over k, right? But I think it would be enough in the exam to just rationalize, just to say that you've got a geometric series by maybe looking at that one there and getting this, and then you could just say similarly for the other terms. Okay, it's better to do all of it, but I don't think you have to go as far as doing the kth term over the k minus 1th term. So now we're at the point where we've got our geometric series. Right? We're going to write down, make it really clear what we're doing. The common ratio is cis of 2 pi on k. And the sum of the first k terms is z1 plus z2 up to zk. So we can write that with sigma notation. We don't have to do that, but we might as well get comfortable with this. The sum from the first up to the kth term will be, well, I can take out the kth root of w here, and then I'm going to have 1, and 1 is cis 0, so cis 0 plus cis 2 pi on k, and so on, up to cis of 2 k minus 1 pi on k. But my formula for n terms, the sum of n terms, is this. So we'll just park that. So we can write this thing here as the kth root of w times 1 minus my common ratio, cis 2 pi k. Whoops, sorry, not yet. Cis 2 pi divided by k. So this is my common ratio in my geometric series, right? So we found that up here. And that's the key to the problem. That's all to the power of k, because I've got k terms. And now I'm dividing by 1 minus cis 2 pi on k. Let's just take out the bit that we're interested in, which is this bit here. Now I've got a bracket in the wrong place in there that I've just realised. That bracket there goes at the end here. Okay, so it's 1 minus r to the power of n. Let's look at cis to the power of the cis thing to the power of k. So cis 2 pi on k. And again, that is very sloppy there. It's not all of that divided by k. It's this. Sorry guys, I haven't had my coffee yet. By de Moivre's theorem, we know that this is just equal to cis of 2 pi k over k, which is cis of 2 pi, which is here, right, and that's equal to 1. So we've got there, right, the sum of the k roots is equal to this, 1 minus 1 over 1 minus cis of 2 pi on k, which equals 0 as required. So there you go. So I've gone through that. I think I've gone through that really, really slowly, and I've probably, most of you have long since stopped watching. But there are quite a few useful things in there to make sure that you're really, really confident with. So obviously de Moivre's theorem is one of them. And you'll see in here that we're doing de Moivre's theorem not kind of just with like 40 degrees and numbers. We're doing it with general terms in a sequence. And I can't emphasize enough how useful that geometric series idea is. That comes up quite often, and I don't think it's on the formula sheet, but I need to check that. Anyway, there you go, and that should set you up well for next week's complex numbers questions.